Question came up the other day about the TRS-80 Model I game, Olympic Decathlon. What's the farthest distance you can get in the shot put competition? I haven't played the game much before, so it was interesting to take a look at it. But also, the question is a good one for reverse engineering because it's fairly specific, and it seems like it's actually possible to discover this without digging into every little detail of the program. So I downloaded a copy and I can run it on my Model 1 emulator. Just tell TRS-80 GP to go into Model 1 mode and then give it the Olympic Decathlon disk, like so. So it boots up and does its splash screen. Good opportunity to just press F12 and have it go in turbo mode so we can skip over these parts. Give us a bit of instructions on the game. And then we say, no, we're not ready to begin a decathlon because we just want to go into the shot put competition. So now here it explains that basically use the left and up arrow keys to control our arm movement to try and put the shot as far away as possible. So we probably want to try and aim for about a 45-degree angle. I've done this a couple times, but I don't really have the technique down, so I'll just give it a go here. Oh, definitely too high an angle. So we got about 14 meters, which is lower than the 16.8 or 16.9 that seemed to be possible. So I guess the question is, how do we go about answering the question? Well, not sure about answering the question. It's one of those difficult things where we can discover how the program works, but just because you know how the program works doesn't know that you can answer questions like, what's the best distance you can get, or will the program ever halt, or does the program have bugs? But we can at least find some of the details about it. Like, for example, if we could find out where it does the calculations on the distance, then we could, maybe sort of work backwards from that and figure out what's the best possible values you can get to maximize the distance. So how would we go about that? Well, there's a couple ideas that come to mind. The first and easiest thing to note is that distance is in fact shown right on the screen. So somewhere in the code, there's got to be something that, writes that number to the screen. It's going to read the number from somewhere in memory, convert it to ASCII probably, and put it on screen. The other angle we could take is more of a bottom-up approach and say, well, we know where the you can find the whether the arrow keys are up or down in memory, and we work kind of bottom up and say, well, let's see whoever looks at the arrow keys and then follow the code forward to see who processes that and what they might use that information to convert it into presumably some kind of X and Y magnitude that goes into the motion of the arm. And like anything, there's a real best answer as to what approach works. The top down is appealing in the sense that you're definitely looking at where you want to be, or in our case, as close we want to be. We want to know about what influences distance, but of course the real question is, what's the most you can get? But let's just try and solve the problem we can, and we know it'll be helpful to solve the final problem. Bottom up could get confusing because there could be a generic routine which reads the keyboard and stores the values in memory, and then some other routine picks up the memory locations, and so you have a bit more of a trail to follow. On the other hand, there's a good chance it might tell us exactly how the keyboard inputs influence things. But I think the thing to do is to let's see where these height and distance parameters are displayed on screen. Now, one thing we could do is just make a copy of the screen, and I'll run up my editor here and paste it in. And since we know where the screen starts, so this top left corner is the location 300 hex or 1515360 decimal. We can see it's down at line 13 or 12 times 64, and then it's 1, 2, 3, it's on the fourth character. So we can compute the exact address of that, but there's perhaps no need to do that. We don't have to go to that much work. So what we can do is run our debugger here and say, you know what? Let's just stop it so we can think about what's going on. Not necessary. We can actually put breakpoints on memory writes. So we can set that so that it's anywhere from 3C00 up to 3FFF, anywhere on screen. Say, okay, we're going to set a breakpoint there and just go ahead and run. We can see that, in fact, that it continues to run, so it's obviously not running to the screen at this point. Now, if we press clear, imagine, so yes, the program stops because it sees it, here in the middle of a LDIR block move instruction, it's running to the screen. 3C01. I see HL is at 4081, so DE is a destination address, so it's running to the top of the screen, and if we click go, of course, it'll stay on this LDIR for quite some time. If we do this, we'll kind of miss our chance to see maybe where that height was written. So that's maybe going to be a little bit difficult. We could perhaps give the specific address for height. But one thing that's actually maybe most useful is just to get an idea of what the code is, what code is being executed at this point. So let's go into the record menu and record something like bus use. And what this will do is give us basically a disassembly of the code and data that's being accessed while this thing is in operation. Let's fire that up. Now go ahead and attempt to do a somewhat better throw. Nope, still terrible, worse than ever. That's okay. So right now you can see it's indicating that it's doing a bus use recording, and so it's keeping track of where the Z80 is executing and all the instructions and data it's accessing, and put it into assembly usable form. So turn that off, and it asks the same, and we'll just call this toss1.txt. Save it. Okay, so let's take a look at toss1.txt. And there's a bit describing what it is, but it's essentially a disassembly. Although you notice it has all the lines commented out, but that's not terribly relevant. And what it includes is like, oh, here we see this distance here, and so on. And it's like, well, that's there's height, and in fact, this memory here you see is 3F01. This is on that. This is the actual video display memory because it's been written to, so I wanted to make a note of it. So you can actually see that 3F03 is where the height actually is on screen. Let's go to 8 wide tab stop so everything's all nice and formatted properly. And so since we recorded everything that's happening in here, well, our answer is probably somewhere in here. But, you know, it's 3,000 lines of assembler and data, so it's a little bit like a needle in a haystack. But this at least gives us an idea of we've got sort of a one signpost as to here our problem lies somewhere within this file. I think they're, let's see. What should we do next? Now, let's just search in here and see where height appears. It appears here on the screen. It also appears here, right here at memory location 5942. In fact, we see the distance appears down here. So this 5942 might be interesting. Let's see if it appears anywhere else. Am I searching for it? Nope. How about, well, seems to be a gap in the memory here because there's probably you know, other data or something in there which is not used by this particular part of the program. So let's look for this 593F. Aha. So here we see that here's something that is loading up 593F and calling another subroutine. So that's probably what's printing the actual height message. We can look at this guy here. What's this 5? Here I'm just going to open up a little file to keep track of some of these things that I'm never going to remember. So what do we got? We got 539F is the height message, and we think maybe 5TBD is some kind of print subroutine. So look, it's now these addresses here are printed in underscores. So if we actually search for underscore 5, if you search for 5DBDB, whoops, 5DBD, get a few hits. But this one here with the address off to the right, this is, you know, definitely the subroutine here. So it reads that byte. It reads another byte. Let's putting these into let's see. Then so the first byte is put into BC. And then the next word is put into DE. Oh, and then we just do a copy. Oh, okay, so let's go back to that 539F. Oops, did I have that wrong? 593F. Oh, okay, so we see it this first byte here, which is loaded into BC. That's the length of the block move. So this thing is 17 characters long, and it's put at location 3F, and then here's the actual 11 characters. So this is kind of useful in that the user, the caller of that, where was he? This here, we know what this does. This is this prints the height right there. We notice that it immediately makes another call to that, so it just sort of, the load is going to move HL to the end of it, so this is going to print the message which is after the 593F. If I change this to a label like this, I can use one feature of the VI editor, which is super handy, which is you just press star on something, it will find the next occurrence of it. So if I press star on HL, it'll say it'll find HL. So I've got this 593F, and the memory locations are labeled with the underscore. So now if I press star, it'll just jump straight to there. So I can kind of hop around a bit more easily than I might otherwise. So yeah, certainly after that we see that, yeah, the distance message appears after it, as we'd expect. And interesting feature here, and that the distance is actually, you would expect this message just to be sort of, you know, a static message. Oh, here's the distance thing, and then we're going to find the height and print it afterwards. But oddly enough, it's right there now. 17 characters. So if we move 17 to the right, we see that, yeah, that thing not only prints the distance string, but it actually prints the entire distance. So something must be writing the distance into there. Yeah, I thought I might actually find that, well, maybe some of this sort of, just by guessing, you might think some of this code up here is responsible maybe for writing the distance. But it's printed right there in the string. So whoever writes to that string is going to tell us where they might give us an idea of where we are. So let's go back to that particular string. So from somewhere in this area here is a guy who knows what the distance is and is converting it to ASCII. So let's go into the debugger and let's set another memory write breakpoint. And this time we're going to do it from 59553 to 5966. Turn it on. Now we'll just press clear. Oh, and here's the guy who's just getting it here. This 737F, we're writing to, or writing directly to 5961. Okay, so somebody's writing 737F writes here. Let's make a note of that. So we should be able to find 737F. And I'll put an underscore on it. Oops, it has to be in lowercase. Huh. We're just grabbing HL from some other location and we're just sticking it in there, and then and it looks like we're also copying from a nearby location. Stick it in there. Oh, and look, I just noticed that's right above the routine that's printing the actual height. So my guess was right. The code was there, but you know, looking at these numbers, it offhand isn't obvious that they're related. It's pretty straightforward. So that 5916, 5961. That's actually space then 2. So that's the kind of the integer part of the distance, I would suppose. And what's the force? Oops, not that one, but it's a 5964. So that's the fractional part. Okay, so but this has already been converted to ASCII. So the expectation is that the number itself is probably, could be a floating point number, but I suspect it's a fixed point number, but it may not be even that, because when you think about the distance, you're really, making a computation where you're just adding to it. So you could be doing that directly in ASCII. It doesn't necessarily have to be in binary, and saves a lot of trouble if you do it that way. But more to the point is, we now know that 469E that's the distance units, and 46AO is the distance fraction or decimal, I guess. I guess it's the tenths. Now I notice here that this we're loading DE with the 469D. And then 469E and 46. Okay, so I'm really curious what this 469D subroutine does. Sorry, that's just the memory location. Oh, okay, that has a space there. We see actually 232. Okay, so that is the distance in ASCII as we knew it would be. So this 5C40. Now, just for fun, if we just turn off this thing and go again. Oops. Debugger lets us display any memory location, so we can actually look at 469D. which is zeroed out again because we started. But now if we initiate another throw, well, that was better. I actually see the decimal number here incrementing. It's 10, it's 12.51, and there the distance is 12.5. So 469D. Who writes to that? Oh, okay, that's fun. We only get 3 chances then in our practice session. We have to continue on it. We've hit a break point, but this could have nothing to do with the thing. So we say, no, we're not ready to begin the decathlon. Let's practice shot put again. Okay, let's turn on our break point and start. We're immediately hit. So 5C72. Let's go look at the code. Now we could of course set a breakpoint at 5C72. And use a disassembler to step through things, but I find that the sort of more complete disassembly we get from bus use is a little easier to kind of understand and orient yourself. So it's loading A with something and putting it in DE, and then it's jumping somewhere. Now it's going ahead to this location. Or where we get to 5C62. Yeah, so this is a subroutine. Well, actually, got to remember my own thing here. See this C here? It says that this this location was the target of a call instruction, so it's naturally a subroutine, as is, for that matter, this down here has also got a C indicating it's a call. So there's some little subroutine we're calling. This compare with 30 hex, which is that's 0, so that's starting to feel like it does have something to do with decimal math. Yeah, ideally when you're reverse engineering something, you'd really like to get an idea of what's going on without having to understand the whole program. So this question is, how much of this routine do we really need to understand? Anyhow, this is writing into DE, so how do we get there? Well, one thing we can do actually is we're at this breakpoint, and so we can hit the record button and do a backtrace, which shows us to say it's before we hit 5C72. So what is this? Some 80,000 instructions that happened before we got to this memory location. So we see there at the bottom of 5C72 is where we're storing it, and then we're sort of, going backwards in time here. reason I wanted to do this is that this actually, if we look back, we can see that 469D is where it loaded DE, which is again at 7350, which I seem to recall. Oh, no, it's up here. It's again right here. So it's like here we're converting 5C40. Huh. This is repeated for some reason. Yeah, look at that, same code. I wonder why that is. Well, I think we can make the assumption here that if you look at 469D, or sorry, 5C40, it's probably, you kind of get the feeling HL as a parameter. I don't know what's happening here too, because here we load HL with 0, and then we shift it right, which is apparently pointless because we know what that calculation is going to be. What's happening right now with 7349 in memory? It is load HL with 0 still. I wonder, logically you expect that this might change, although but the disassembly would, the bus trace would actually make a note of this for self-modifying code of some description. the thing that really comes to mind is what's going on with this 469E. No, again, it's after it's happened. What is this 464E about? Well, I'm just going to keep a watch on 464E. See what it's up to. Turn off our breakpoints for now. Let's run free. Well, 464E is changing. Started to speed up there. Yeah, and also I noticed now we've got this 1 appearing in here, this 119. 19 is going to be 16, 26. So I have a feeling this 464E is a distance. Now we can search that in the disassembly, although it's often nice to switch strategies from time to time and instead say, well, if 464E is a distance, maybe we can just change that and change the distance. So I think this thing is the high part here. So let's change it to something like, let's change it to 5, see what happens. If it's the kind of the root or the source of the distance, and we might actually see the distance change on screen from that 1.3 meters, or it might just get wiped out. It means that it's only an intermediate value. So let's have this thing go on. Doesn't, looks like it changed the height. Huh, okay, so that's probably the height. Well, that's interesting. We will probably, having teleported our shot put up a few meters, it's probably going to go a lot farther. I wonder if we can change these values now. So this is the height. What if we... Yeah, it's not updating them. Okay, so let's initiate another go around here. What if I change this one too? Yep, I don't know. say that 464E 46 F1 is definitely the distance. So there we go. We got a rather spectacular shot just by a little cheating. Also notice, which was as mentioned, is that if you get past a certain distance, you get this all right indication. Which could be another handle into the problem. Because whoever displays the all right probably knows about comparing the distance, but who knows if it gets to the source value. But now that we know that 46 F1 is the distance, then we should be able to, chances are we can find that in the code. But we don't. 464E. Oh, because it's not 46F1, it's 4651. Looking at this here, it suggests that maybe 4650 is what's referenced. Yeah, that's because my calculation is wrong. Just sort of flipping through here, we can see that here we have a reference to the distance. Here's another part where it comes up. And again. Which we've been through this before. If I replace these, I can quickly find them. So anyhow, the disassembly and the fact that we can change the value and actually have it change in the program means we've found the distance. We've really seen it, and we don't just think it is. We've verified that that is the distance traveled. So now the thing to do, maybe step back for a second and say, so again, we want to know what the maximum distance is. Well, can't answer that yet, but we can see who in fact is making changes to the distance. Look at this one here. It's reading the distance and then it's doubling it, calling some subroutine. Here's another one where it's reading the distance and calling that same subroutine. This one, it's adding a constant. That actually looks like -9, and adding it to the distance. Oh, I see. If the distance is Oh, I get it. If the distance is below a certain value, -9, I guess, then it's going just to print it as 0. Oh, okay, that explains that code because it's jumping over it here. Well, that's nice to know. We'll make a note here if it's too small, then print 0. A duplicated code at the end kind of bothers me, but best not to get distracted, as it doesn't really matter. It's a different question. So this routine here, you know, here it's actually adding some value to the distance. So what? What is that value? Four, 6. It's like adding -10 to it. Four, 6, 4A. What is 4, 6, 4A? Four, 6, 4E. So this is the height. It's 464C. Four C, 4, 6, 4E. Right, 4, 6. So there's the height. Well, kind of squint at this a little bit. It does seem like it's a kind of a physicsy calculation. You know, maybe we're 464A might be the y component of the velocity, because it sort of stands to reason that for gravity you're going to keep subtracting from the y to simulate that effect. Now, if that were the case, then 464A might be, that is y velocity, maybe. Then if we muck with that while the ball is in flight, we might see something happening. Okay, so let's do another. Oops, terrible toss. So yeah, what is it? 46. Huh, what do you know? 464E. 464A. Let's take a look at it a little bit. Height's still increasing. That's still a positive value. Then yeah, we see it's coming down. It's a negative value. So if we change this, change it back to that sort of 400 positive value again, and then we see the height go up again. So I think that is the y velocity. If that's the y velocity, then you just got to think that this is the 464C is the x velocity. Which seems to be negative. Not surprising, we've got zero distance and my throw is terrible. Well, let's change it to a positive value. Ooh. Oops, that was not. Numbers went quite strange there, didn't they? And it's not. I didn't change the right 464C. No, I did. Okay. Oh yeah, I get a lot of points for that completely bogus throw. Darn it. I didn't want to restart the decathlon. Let's just hit the reset button and see what happens. take the debugger down so things run a bit faster. No, I'm not ready to begin Decathlon. I do want to practice the shot put. C. I'm going to push it up a little bit, but then I'm mostly going to do right arrow. Yeah, 385. Well, let's alter that. Huge value. Let's just triple it. Let's see. Didn't change. Well, if those are the X and Y velocity, as I suspect, then Y velocity is going to change, but really, as we saw, the X velocity isn't going to be changing once you release the ball. Physics will dictate if the ball's going up or down and change the Y, but the X is going to be fixed. So whoever is writing 464C, probably going to be a result of the arrow key. So let's put a right breakpoint on 464C. See where that happens. Put a little note here that this is probably the shot put physics update. And I suspect this subroutine call, the subroutine calls in here are going to be critical because they probably go through some of the more complicated machinations to figure out the actual physical properties, which will be important. We want to know what the ultimate distance is. So yeah, we've got a memory write breakpoint on 464C. So let's see who writes that. Hmm. 62E9. Not actually on our little trace here, which is suggests that it's probably initialization code. I mean, it is writing a 0 to it, so let's pretend that's okay. Nope. Guess again, it's always being hit. I really didn't see it in here, huh? Still, I'm not convinced. Let's just get back into our mode here. There we go. It's not being hit at the moment. As soon as I press the up key, it is 704C. Really? What? my my range was wrong, or my top range was wrong on there, so I think I was getting a lot of, there we go, 7104. Well, that's definitely going to be writing a 7. Uh, 464C, 463E. Makes a call to this 5B7E, then writes a result. Oh, okay. Complements. Minus it goes to here. Oh, A is either going to, oh, okay, if A is, why do they complement it? It just seems to complicate things. I mean, whatever the value of A is, it's going to pick between subtracting or adding DE to HL. Four, 6, 3E. Okay. HL plus or minus DE, depending on A. So I mean, this 463E seems important. So let's off screen. Fine. 464E. Let's see who writes to that. No. 463E. All these crazy numbers you have to get exactly right. You don't get the thing you want. So presumably I hit the again. 463E, get it right. Two FA. Well, this 5C34. Note of that. Clears A. Almost always. Something else that happens, but it doesn't show us because it doesn't show us where the Z80 didn't go, so it never came into here. Just clears A and stores it. Huh. Well, we're getting closer at least to figuring out how the physics of this thing works. Getting some values figured out as to some of the parameters and so on. So getting us a better idea of what might be happening, but we still don't know the exact answer to the question yet. I think for now I'm going to take a break and then come back to this and see how far I can get in unraveling some of the more of the mechanics of it, get closer to answering the question of what's the maximum distance you can throw the shot put. All right, let's get back to this. Things seem to be getting a little bit confusing here, so I'm think that perhaps tackling this a bit bottom up might give us some insight as to the adjustments of the velocity by the keyboard input. See what's happening here in the emulator. I'm still in the middle of things. So what we'll do is we'll turn off that memory write breakpoint and set a memory read breakpoint on the arrow key address, which is 3840 hex, and see what that hits. So there we see it's 6164. It's reading it, combining it with something, and then stuffing it in 4683. Which didn't 4683 come up before? Oh, quite a few loads of it. Make a note that 683 is arrow keys. Maybe not quite the arrow keys because it's storing something on there together, but using the alternate register set. Well, 615F, we'll say this is the pull arrow keys. Let's see where we find about that. A few places where it's called here. It's interesting that it's combining them. Almost suggests that once a key is hit, it's down. I guess that doesn't matter too much about the subroutine. It's the fact that 4683 is kind of a key location. Here we write it for some reason. Bit 3 of A. Oh, okay. Let me take a look at, remind myself of what the keyboard matrix keys are again. Bit 3. So bit 3 is the up arrow key. And bit 5, 0, 1, 2, 3, 4, 5 is the left arrow key. Kind of clearing it there, so that's kind of strange, and we're definitely in some kind of loop here, looking at the arrow keys. Let's see if we can follow along the story. So it's like, if the arrow isn't keyed, and then jump to 706C. Otherwise, if we have the up arrow, then we take 128, load DE with 4648, subtract DE from HL, then double it, and then change it. Okay. What does the left arrow do? Oh, let's call some subroutine. Saves it. Calls another subroutine. Again, doubling things around. 32 hex. 50 decimal. Interesting number. Change that to 50 since it feels like it's a more realistic value. Again, this to make a note about this being the shot put input. Yeah, it's interesting. The 4648 is, you know, it's in the same kind of memory as some of our other numbers. So it feels like getting close to bridging the gap between the low and the high level. So it's kind of like up accumulation or something. I like to stick in the question marks just to know that we don't know what that is yet. That's what we think it is. Where's this one? Again, 4648 comes up. Four, 6, 7, 4 also plays a part in this. We have these routines like 5B69. Grabs a value into HL, doubles it. That's 46A9. Ah, okay, this is some kind of table lookup. Four, 6A9. Not appearing here, so let's take a look at the 46A9. You can see increasing values. A word table. looks sort of like a multiplication, actually. It's because I mean the F5 is fairly constant here. And then the lower value is increasing. 5, F4, F4, F3, 3, 1, 2, 3, 4, 6, 7, 9, 10, 12, 13, 15. I'm not sure what the relationship is. Just using 5B96. B69. Comes up in a few places, so obviously fairly generic code. It stores result in 4639 and 463B. Aren't immediately used. It's interesting if you look at the addresses here, because you kind of do get the sense that there's the lower level subroutines are at the top of memory, and as we go down we get into sort of more specific things like the shot put physics. But I see it is calling 70D7 7122. Oh, that's the shot put physics update right there. So what's the 70D7 then? What's that doing? Loading value is subtracting. If there's carry, then we do something, otherwise we negate it. We add 128, flip it over, call something. Divide HL by 2, and then call something, and on it goes. Here again, we're operating, of course, in the area. We've got 4640 is in play. Just a little bit before. A little bit. And a little bit before that up accumulator. curious if this is the actual main loop of the thing. I mean, do we hit 7093 all the time? Let's set our breakpoint at 7093 and see what happens. Oh, there we seem to hit it maybe at the point we're actually releasing the shot put. So this is the perhaps the main loop. If you look at the stack here, it returns to 702A. I guess we kind of knew that. Yeah, there's the call. So the 704C take a so we call 7094. And 7394, and then only DE with a destination address. So I think you get the feeling that if we step over this call, that it's probably going to run until the shot put maybe leaves the screen, maybe until it actually lands. Yeah, there we go. This is like this is the shot put throw, and this is the shot put going through air. And what do you think 7394 is? Let's step over it and see. 7394, definitely a looks like that's just displaying it. I notice the call here is if we step over that. Yeah, this is the I'm just pressing the clear and waiting for it to continue. In fact, you can see that 67AB is just a little loop here that's waiting for the clear key to be pressed. We definitely know where the routines are, which are reading the keyboard input and manipulating variables and updating the physics of the shot put, which is pretty critical information. Of course, it's still a long ways away from answering the actual question, which is how far can you make it go? And for that, I think we're going to have to really sit down and unravel these routines and look at how they work, because ultimately we're going to need some model of this code, so, you know, as to how the physics works, some kind of equation or something which says based on certain inputs what the distance will be, and then once we have that, we can then figure out how to maximize that distance based, or how to set the input to maximize distance. And then ultimately we would be able to test it in that we could change the keyboard input routines to actually play back scripted values and verify that they get the right results, or run the code in a standalone test bed. The animation and stuff, which is must be a pretty nice bit of line drawing in there to do the arms and so on, is nice and all, but really it just come down to a pure numerical question. So I think for that I'll leave it for now, and maybe get back to this later to once I've come up with more of an actual answer to the question. Right now it's just been kind of an exploration to see what we can find, and I think we found sufficient signposts, and we'll be able to figure out the rest of it in reasonably short order. But it'll be much easier than trying to record the process and think on the fly. So until then, we'll see you later.